Okay, welcome.
Okay, so very good evening and happy that even on a weekend we all are here to learn something in next couple of hours. Today will be quite interesting topic that is distribution network reliability. First of all, there are two terms which are very important. One is known as reliable and the other term is known as resilience. You must have heard the very important term of 2025, which is known as power system resilience and very specific to distribution smart grids. So, smart grid is a system or it's a distribution system which is considered to be more resilient in nature. So, many people may ask what is the difference between a distribution system that we experience today and how does it differ from a conventional smart grid? The only difference to me, and very important difference, that the smart grid is more reliable and become resilient compared to a conventional distribution system. That means there are few features that a distribution system can behave like a robust distribution system because of an environment is known as smart grid to me. So we have a conventional distribution system, we have a smart grid. To me, the same line, same substation, same PV, everything is fine. But what is that extra that makes my smart grid different than a distribution system? That is, the distribution network become more reliable and resilient. Okay? Resilient means the network will come back to its originality even after a fault. Reliable means it is expected to deliver even under worst condition, isn't it? So this is because reliable, resilient, they're all close terms. So then I thought it is important to include distribution network reliability into advanced smart grids. Normally we don't study, we believe that is fine. But a person who is working in smart grid must know bit of reliability, bit of resiliency, bit of distribution system load flow, and bit of a distribution system operation and control is mandatory. So today we will be focusing mainly on distribution network reliability. Uh, First of all, I will try to understand what is reliability analysis. Then we'll get into probabilistic failure analysis of network components, reliability matrices, then value of loss load calculation. If there is a load loss in a system, which is very commonly seen, for example, today if there is a power cut for 2 hours a day during summer, we feel it is acceptable. It is granted, but it is not so. You must calculate the loss that we have faced because of energy unavailability. That has never been calculated. Once you calculate, it is mind-boggling where you'll see millions of rupees of loss because of couple of hours, no access to electricity. Am I right? So, system reliability enhancement technology, and we'll see what best can be done. Now, first of all, introduction to reliability analysis. Reliability and adequacy, because here we carry a lot of confusion with us. I think that need to be clarified today. Uh, Sorry. Uh, so when you talk about reliability and adequacy, so adequacy and reliability define two separate but independent concepts. The term reliability describes the security of the system and the avoidance of power outage. All right. Sorry.
राइट नमस्कार तो बेबी को फोन को कॉल कर हो चलो ठीक 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 नमस्कार एक्चुअली मैं वो इग्नोर
Whenever there is a call, I pick it up. Okay, sorry about it. So when you talk about reliability, uh, they describe the security of the system and the avoidance of power outage, whereas the term adequacy refers to having sufficient system capacity to supply the electric energy requirement of the customer. Adequacy means the system is adequate enough to cater
the
the
consumers.
consumers, means it has enough excess things capacity to offer.
Reliability
Reliability means
it
it
can,
can, if the system is secure enough during a outage. There is a line outage, we say still my customer will get power.
that
That
is
is known as
reliability.
reliability. Even the load increases, still you are getting power. That is adequacy. Okay? If the substation transformer fails, the village get electricity, that is reliable. Even during summer peak, the village is getting power, that is adequacy. And even if there is a fault, within a second the village is getting power, is the resilience. Reliability, adequacy, and resilience. All right? And all three are part of your smart grid concept. Although these are adequate methods for evaluating distribution system reliability, there are insufficient data on reliability performance to identify the most cost-effective distribution investment. All right. We really do not know how much money I have to invest to make the system extremely reliable, and almost that is not known to anybody. Because whatever you do, for example, you eat perfectly in time, you do exercise perfectly in time, you measure your food and eat, you maintain your stress level, you take enough supplement vitamins, you do everything, but still you may get a heart attack, am I right? That's similar to that. You cannot make your system 100% reliable. You may say, there is one line. You say, if I put two, that system become reliable. But it may so happen both the lines fails. The probability increases. When I put three, again all three may fail. If I put four, all four also may fail. So making a system 100% reliable is next to impossible. But nevertheless, we can optimize the investment so that it is more and more reliable to the system. Most distribution interruptions are initiated by severe weather-related interruptions. Now, instead of one transformer, you say, I will put three transformers, so that n-2 contingency is met. But there is a cyclone, it will take all three transformers 2 kilometers away. So all your investment is not going to work. That's why whenever there is a weather-related interruption, with a major contributor being inadequate maintenance, distribution system reliability can be improved by the timely identification and response to the failure. But irrespective of those natural calamities, above and all, we need to still make the system 100% reliable, where we need to know the life of the conductor, the life of the capacitor, the life of transformers, the life of the poles, isn't it? So if you do predict well before the life of every element, there is a pole we see in the street, and almost the basement is rusted and about to fall, but still we watch, one day it will fall, and 3 days there is no electricity to the village, and then fourth day we get it. But if I would have predicted and changed it well before time, so my system become completely collapsed. Now, these are the challenges: classification of generic and specific cause of outages. Why we don't get electricity? Okay. First of all, the category is called weather-based, where you can have snow, cold, flood, heat, hurricane, ice, lightning, rain, tornado, wind, and others. So these are the effects actually, very natural. However, in case of system components, it could be electrical mechanical failure, could be insulation failure, could be voltage control equipment failure, could be protection and control failure. And you can see, when I say electrical and mechanical failure, probably that could be your fuel supply, generating unit failure, transformer failure, switchgear failure, conductor failure, tower pole attachment failure, as I was mentioning just now. And moving to insulation failure, it could be in transmission, substation, surge, and cable. Voltage, it could be voltage regulator, tap changer, capacitor, reactors. And when I say protection, it could be relay, could be communication signal, it could be supervisor control errors. So these are the scope, 100 of scope actually where the system may fail. Now, in case of specific outages, could be, um, the reasons, the causes we say, there could be, uh, an animal short circuiting, an elephant touch your distribution system 11 kV or 33 kV line, that is a failure. Could be a vehicle accident, could be a fire, could be a, tree falls, and there are so many other reasons. And then there could be actually system conditions like stability issues, public like, commercial industrial issues with consumers, voltage reduction issue, utility personnel, issue, sometimes the operators are not up to the mark. So many reasons that are given actually how the system can lead to unreliable system subject to failure of those components. Now, if I derive some diagram, classification of generic and specific causes of outage, one thing is very, very clear. You see, the A is based on type of event, B is generic subsystem, and third is actually generic causes. For example, if you concentrate on the last one, it very clearly says that 46% of failure is due to system operation, and 29% is due to components, and 15% due to weather, and 10% unknown, right? Similarly, if you see, in case of generation level, transmission level, and distribution level, it is 55% related to generation level, 35% related to transmission level, 38% and 7% related to distribution system. Most of the failures, yeah.
After such classification, still there are no factors.
Yeah, could be. There could be some factors that we do not know. Am I right? But most of the things have been taken care. Most of the things are taken care. Yeah. Customer outage, reduction, and hazards, they are actually 10%. But one thing is very clear, the generation is very much prone to failures. Transmission is next, distribution is third. Okay. And how they calculate those failures is based on the magnitude. If there is a transmission line failure, then it fails most of your distribution networks. So one transmission line fail means almost 200 substations failed. But if one distribution transformer fail means a small load is being failed. Are you clear? So that's why actually when you go backwards from distribution to transmission to generation, the failures actually keep on increasing. Now, reliability and cost trade-off in distribution system, because one thing is very loud and clear, if you like to make your system reliable, then you have to invest money. I guess I told you one story in the past, probably. I was working on a distribution system of United Kingdom, where when I was analyzing the data, I could see most of the substations do have 3 transformers. So then I talked to the distribution company and asked, well, I think there is some mistake because most of the substations do have 3 transformers, which is not true. They said, no, in the UK, most of the distribution system do have 3 transformers. But in India, we have actually how many transformers in a distribution system? Most of the distribution systems, we do have either 1 or 2. Means 1 means there is no contingency, 2 means there is n-1 contingency. But when they have 3, means they n-2 contingency, means even 2 transformer fails at any given point of time, which is less likely, still they will be able to get a power. Okay, which is the rarest of the rare. Okay, so defining appropriate reliability. So how much you have to invest so that the system become reliable, and with minimum investment, can you make the system maximum reliable? That is the question. So it is neither feasible nor economical to avoid all severe interruptions. Okay, it is not a good idea to invest too much to make sure the system is not going to fail. That is not a good idea. So the appropriate reliability occurs when the cost of avoiding additional interruptions is higher than the cost of interruption themselves. Optimal reliability is reached when the sum of supply cost and interruption cost is minimized. Investment in reliability does not yield linear improvement, diminishing return supply. Now, if you go for cost effective consideration, focus should not just be on absolute reliability levels, but on the incremental benefit per dollar invested. So, if you spend a dollar or a rupee, you must know how much increment in the reliability being achieved. Key questions: where should the next rupee go to achieve maximum reliability gain? If you have X million with you, you cannot spend everywhere. So you have to focus what are those areas I must focus to make the system more reliable. So aside from reconfiguration and sectionalizing, the main operational method to enhance reliability is timely repair of failed equipments to minimize outage duration. So what is the final conclusion comes to be? Maintenance become one of the very, very important aspects in any system reliability. Okay, many times we say, "Ki buy this new device, buy this, everything is fine." You cannot make the building more reliable by making big and big, but you can make the system reliable by maintaining whatever little we have and working it in a proper order. Otherwise, even if I give you 5 laptops, tomorrow you will have a point where you will not have any computer with you. But even with one laptop, you can continue forever if you are maintaining it properly. Am I right? That is the fact, am I right? So, as reliability improves, maintenance cost decreases. So once you maintain, then the reliability will improve, and once it is reliable, then the maintenance cost will reduce. When the system is in order, you need not invest anymore. So customer damage cost from outages will be seriously reduced. Customer satisfaction also rises with system reliability. So there is an optimal reliability level. There is an optimal reliability level where investment yields maximum cost effectiveness by minimizing customer damage cost from supply interruptions. Okay, so we need to understand what is that optimal reliability level where investment makes a very cost-effective mechanism for the customer to avoid damage costs. That is very, very important. And how do we calculate? Nobody knows it. Probably end of this lecture, today we'll decide if I have 100 crores with me in Jaipur distribution system, I'll tell you where to go and invest. All right. So first of all, when you plot a characteristic which is cost versus reliability curve, I think the right hand side characteristic is very important. It is y-axis is my cost and x-axis is my system reliability. And you can see that the investment cost characteristic you can see, and then you can see your cost of interruptions. Okay, so cost of interruptions will be more when the system reliability is more. So the characteristic is keep on reducing exponentially. And investment cost will be keep on increasing when you like to achieve 100% reliability. Now, what happens actually when you add both, you will get the total cost function. And in that total cost function, you have to decide what is my optimal system reliability point. And that will give me the optimal cost, okay, to achieve a certain amount of reliability. So you need to know what is cost of interruption, You need to know what is cost of investment to achieve more reliability. Then you understand total cost. And for an optimal percentage of reliability, you will get how much money need to be invested. Okay. So this figure illustrates the relationship between investment in system reliability, the resulting level of reliability, total cost, which is supply cost plus cost of interruption. As reliability increases, total cost initially decreases, reaches a minimum, and then increases due to higher invest cost. If you see the total cost, that function actually keep on reducing. You come to a minimum point, and then it increases further. So your job is to capture that minimum point, and that is the best because reliabilities keep on increasing and cost is reducing. And after a particular point, to achieve more reliability, the cost is more, that need to be avoided. So the optimal reliability level corresponding to the point of minimum total cost. This confirms the idea that beyond a certain point, improving reliability is not economically justified, right? So this is a very, very important concept for all of you. And now we are moving to, so now we talked about the distribution system. And now we need to know what are the reliability issues, what are the resilient issues, what are the adequacy issues when we have DRs. Why we are doing it? Because in case of my smart grid or in advanced smart grid, I will have a distribution system along with renewable energies. So if I do not calculate reliability because of the renewable energy sources, probably I am not doing justice to my smart grid reliability. So indirectly what you are learning here is the reliability related to smart distribution system or smart grid or advanced smart grid. So this is the beauty of today's lecture, where the renewable energy sources such as wind and solar affect power system reliability in both positive and challenging way. As of now, what we have concluded, the moment you have renewable energy, the system losses will reduce. Like that, actually, we have taken the positivity out of it. But now we are saying, because of renewable energy, the system reliability may improve or may suffer. So primarily due to their variable and stochastic nature. Okay, so what are the reliability challenges because of benefits because of renewable energy sources? Improved system redundancy. Okay, that means adding distributed renewable energy sources increases the number of generations, which can reduce the frequency and duration of outages at distribution load points. Means we are thinking that we have 100 megawatt. If I can put 20 megawatt of renewable, so probably I am increasing more redundancy, means extra, okay, energy actually I am putting into my system. Support for load during grid disturbances, okay. Now, what is happening when integrated with energy storages or hybrid systems? I have a storage devices. When the grid is oscillating, this battery can help that unbalance to be sorted out. And then decentralize, that is distribution renewable, reduce the dependency on long distance transmission, improves local reliability. So, instead of getting all the power 2000 miles away, you can have local generations within 5 to 10 miles. Now, what are the negativities? The first important challenge is with intermittency and unpredictability. So, renewable energy sources are not reliable. Renewable energy sources are not reliable. Sometimes it will give, sometimes it will not. Increase complexity in system operation. Okay, so lot of challenges. Control, operation, power tracking, maximum power tracking, so on and so forth. Reduced inertia and frequency response, that is another challenge. Risk of energy not supplied is also a challenge. Let's say for a cloudy day and all my PV panels actually stop generating, right? So these are the issues actually. It may look very beautiful to make your smart grid with renewable, but when you look at reliability, these are the accept actually need to be taken care. Now, one more important part about actually communication technology. Now, the moment I say it is a smart grid, means it is a distribution system plus renewable energy. We have seen the challenges related to renewable energy. Now we are putting actually smart communication. Smart grid means it will be having enough communication. And how the system is going to be reliable because of communication and non-reliable because of communication, that need to be seen. So the positive impact, that is enhancement of reliability, area, contribution of ICT, information and communication technology, monitoring and control, real-time monitoring via PMUs, SCADA, BAMs, enhances situation awareness. So these are the positive things because of a ICT arrangement, automation and self-healing, faster detection and isolation of fault with intelligent relays and automation systems, demand response and DR integration, better control of load and distributed energy sources, improving system adequacy and resilience, reduced outage duration. ICT reduces frequency and duration of outages, improving SAIDI and safety indices, flexibility and scalability. Must have enables dynamic reconfiguration, load forecasting, and DR coordination. Now, moving to negative impact, cyber power interdependencies, direct interdependency. Failure in ICT can cause direct failure in power components. Example, EMU failure, CV failure. Am I right? Indirect independence are actually ICT failure may not immediately impact power system, but make them vulnerable to outages. And finally, but not the last, cyber attack become very, very common. So when we talk about cyber security, cyber attacks, because of smart grid, those problems become very, very visible. Okay. When you don't drive, you don't have any risk. Like this, people say olden days, you be at home, it's fine. So we make the system very modern, and now we see that there are a lot of challenges. Okay. Still, it continues. One is ICT infrastructure failure. Tomorrow, let's say all the networking stops. What will happen in human life? Almost impossible to live. Am I right? And then environmental and weather impacts. Anything, any adverse weather that will seriously damage most of my things. Okay. So weakens the effectiveness of communication, especially in active distribution network, that is ADNs. Okay. Maintenance is central to both reliability and adequacy in power system because it directly affects the health, availability, and performance of system components. Why maintenance is central to reliability? Because maintenance play a key role in this by reducing failure rates, improving component availability, and enabling condition-based interventions and enhancing system security. So these are the four important major achievements by doing a proper maintenance mechanism. And so maintenance is the key to my reliability. Maintenance is the key to my reliability. Now, maintenance support adequacy also. If you do maintenance properly, it is not about reliability. It can also enhance adequacy directly. It is something like you have two vehicles. If you maintain both the vehicles properly, if both the cars are maintained, then you are adequate enough. Either use this and that. Okay, ensuring generation capacity availability, maintaining load serving equipment, supporting demand response and DR integrations, and avoiding energy not being supplied. So I think these are very, very important, points for any maintenance and adequacy, how they are related. Now, these are the classified approaches, how people do maintenance. Now, if I tell Mr. Manmohan, how please do maintain MNIT Jaipur distribution system, what do you do? What to maintain? How to start? You will go one by one, am I right? But there is a method of maintaining any distribution system. And these methods are as given. There is a process. The process are actually stochastic based maintenance approach, linear programming based maintenance approach, meta-heuristic based techniques, control theory based maintenance approach, real-time data based maintenance approach, machine learning based maintenance approach. Am I right? So you have to apply a logic, a technology, and then you maintain actually. Not you randomly go to a particular point and maintain and come back home. So that means, for example, when I talk about stochastic based maintenance, which is very, very common in history, uses probability distribution to model failure and repair behavior. Means if you have a distribution line or an underground cable, you have a history, and that history will guide you which component is prone to failure and what is the priority of a particular component to be maintained. Captures aging and uncertainty, support reliability estimation, and the limitations of this stochastic method is what is that? This
High competition.
cannot be decrypted. There is some message is coming.
He might have sent some smiley. He might have sent some smiley.
Okay.
That is not.
All right, all right. And the limitations are high computational effort, limited in scheduling optimizations. Now, similarly, each and every method, linear programming, meta-heuristic techniques, control theory-based techniques, real-time database techniques, and machine learning-based techniques, each one of them have certain, I think some message is coming. Huh? Audio? There's no audio? Please ask them. Am I audible? Say hello.
Is it audible to you, please?
Who is saying audible? But there is, why so many messages are coming? We can talk to Aniket. Am I audible?
Yes.
Yes.
इसके तो सही आ रहा है.
Okay, there is some issue. All right, very good. So no problem. So we had different kind of messages, so we thought we'll reconfirm it. Okay. So, for example, if I take control theory-based approach for maintenance, so model dynamic behavior of power system and maintenance impact, high accuracy in real-time control and stability enhancement can be achieved, and requires detailed model may not scale well to full systems. I think these are the methods which gives you an idea. The zones and areas and components and devices need to be maintained on a particular order and on priority. So with this, the first section of maintenance we have discussed. Now moving to a probabilistic failure analysis of network components, because we all know that even if you put a device like substation transformer, which is very common to failure, until unless have an idea, what is the probability of this device is going to fail? Most of the time we say it is 0.01, let's say. Okay, in 100 days, 1 day it is going to fail. Similarly, generations we say it is 0.001. In 1,000 days it is going to fail 1 time. Okay, so if you see very closely, in liberalized, especially deregulated electricity market or a modern electricity market, which utilizes, utilities are increasingly focused on optimizing their asset management. As I told you in the past, the moment you privatize the distribution system, they do not want to invest anything on that. They do it only when they believe that this is necessary to be spent. Correct? Am I right? Which is the fact. So balancing reliability with minimum cost become very, very important. reducing capital and maintenance costs become an important thing, and ensuring long-term sustainability of distribution equipments. Like in the past, actually, we had state electricity boards, all become bankrupt. Why? Because they will replace transformers, they will replace poles, they will replace lines. Whoever says they will replace. There is no planning. They become bankrupt. But today, Tata, Reliance, BSES, Rajdhani, they're not, they've become millionaires because they're very smartly maintaining the thing. They know this 1 crore benefit will go to what pocket, what kind of maintenance, who is my customer is very important, who is paying electricity bill correctly to me. State government will put a transformer in a slum area where the bills are not being recovered. But the private company will put it in front of a five-star hotel where the payment is very keen to me. Are you getting me? So, ensuring long-term sustainability of distribution equipment is very, very important. So, in case of distribution system, there are millions of components, cables, transformers, breakers, compared to transmission systems. So maintaining all of them become very, very challenging. But one case study very clearly says monitoring every individual asset is almost infeasible. You cannot monitor due to high cost effort, and it has been estimated that if you do it in Germany to make 100% reliable system, then you have to invest 20 billion pounds or euros, almost a country's economy, just to maintain your distribution system. This leads to reliance on statistical data rather than real-time monitoring and decision making. So you have to have some history to take care of such situations instead of randomly wasting your money and spending here and there. So why is failure analysis of network component necessary? First of all, support asset management decision. Asset management aims to make cost-effective choices for maintenance, replacement, and reinvestment. For these decisions to be accurate, they must be based on historical failure trends and component reliability matrices, improve supply reliability and power quality. Failure in distribution components like transformer, cable, and circuit breaker directly affect power continuity and customer satisfaction. Understanding when and how component fail helps in preventive actions. Once you know when the component is going to fail, then probably I can take some preventive actions. Now, address the aging infrastructure problem. I do not know because to my understanding, I have seen the electric pole which is standing in front of my house is for almost last 50 years. It has never been replaced for last 50 years. And probably it may be there for 20, 30 years prior to my birth. So that means the pole is 70, 75-year-old. Isn't it? So, and you might have witnessed many substation transformers. Also, I witnessed a couple of transformers I have seen, they have never been changed for last 30, 40 years at least. Isn't it? So aging is a very important thing. While the theoretical lifetime of electrical component is close to 40 years. Normally, every component need to be changed after 40 years. Many utilities means after independence, India might not have changed or replaced 50% of the distribution assets, which has been installed at that time. Okay, so operates equipments for beyond this, that is implying a lifetime of 100 years or more based on current reinvestment rate of 1% per year. That means most of the equipments, utilities, utilize even up to 100 years. If you see a generating plant, somehow it is generating for last 80, 90 years. Am I right? So I think we need to understand the aging feature also seriously. And then they are prone to failures. If you allow the man to become extremely old and still work, so one day he will faint, there is no doubt about it. So avoid catastrophic failures, very important. Certain failures occurs without visible warning and without disturbing the network. Proper statistical failure evaluation can identify such hidden risks before they lead to cascading failure outages. Before it becomes catastrophic, okay, we have to be very, very careful and try to understand the system. You should not say, oh, it is working for last 5 years, so it will continue. No, you will face the real challenges until unless. So cost optimization is one of the important target. So reliable failure prediction minimizes unnecessary replacement and unplanned maintenance, optimizing operational and investment cost. Now, very important, now we are getting into mathematics, very important. Evaluation of the failure statistic. How do I evaluate the failure? To collect and evaluate real world historical failure data from distribution network and categorize failure causes and location. What I like to highlight here, we need to collect the data of each and every device across the world. What is the failure rate of cables? What is the failure rate of relays, switch gears, transformers, poles, everything, generators, So once you get those data and their locations, this analysis is essential to build accurate reliability model for various components in the distribution system. Now let's say you get actually there are 100 generators in the whole world got failed before their lifetime, for an example. So that need to be investigated. What is the reason? Whether it is the mechanical failure, insulation failure, electrical failure. Once you analyze, then you know what component or what maintenance strategy for that device need to be adopted by the utility. And that is what the future is. So data collection and scope, the researchers analyze approximately 120,000 historical failure records collected from 1920 to 2005, almost 85 years data being collected. And then these records were obtained from practical operations and maintenance report of distribution network components. Means for 85 years, we collected the components across the world. And then we realized there are 120,000 failures. The failure data includes both disturbances, example fault, and non-disturbing anomalies. For example, when we say line fault, line fault, line fault, but how many times the lines really broken and came to ground? If you know that, then accordingly you can take care, no? So data classification, we have to failure, type of equipment, component where the failure occurs. It could be circuit breaker, transformer, cable, joint, conductor, and then failure cause. Imagine if someone is saying because of the aluminum binding, the conductor fails very frequently. Then I'll go think of actually copper binding or some other material. That is also equally important. So the nature of the failure, whether it is electrical, whether it is mechanical, or something altogether random, nobody knows. That also happens someday. Everything is perfect, but still there is a failure. And that need to be stochastic. That is stochastic. So if I drop the failure statistic, which is very, very important, I need your attention here. Now let's say in the first case, which is the overhead line, and overhead line actually, the conductor, which is normally the probability of failure is 67% of conductors in overhead line today. And out of which 33% become random failure and 64% is become mechanical and 3% is going to be electrical. So whenever there is a conductor failed, I need not waste my money or analysis and time to understand the electric failure of these conductors. Because all the conductors fail because of mechanical in nature. So I have to focus on mechanical property of this conductor, how they have been arranged, how they've been, placed. Now similarly cable, paper cable, BP cable, joint cable, termination cables. Now out of which you could see there is one thing, for example, paper cable if I say, paper cable 60% failures related to electrical and there is no mechanical failure. Then why do I waste my time focusing on mechanical failure of paper cable? Whether it is strong, whether it is strength, waste of time in maintaining it. So this is how actually each and every secondary substations. For example, if I talk about actually transformers, 48% is going to be mechanical, 32% is going to be electrical. In case of switch gear, in case of circuit breaker, 85% is going to be mechanical failure. There is nothing to do with electrical here. Right? So percentage indicates the proportion of total failure attributed to the given cause for that component. So what are the key observations? Overhead conductors, primarily mechanical failures. Cables, failure mostly due to electrical degradation. Cables, very high percentage of electrical failures. Transformer, distribution and transmission transformers. Distribution transformers fail due to oil leakage, electrical issue and impulse voltages. Transmission transformers fail mainly due to mechanical stress. Circuit breakers fail due to mechanical. Disconnectors because of aging and mechanical cycling. So once you know this analysis, especially for any distribution system, these are the factors need to be calculated, and hence the maintenance approach and reliability study and investment need to be planned. Identifying dominant failure causes help utility to design targeted maintenance program, plan component replacement, forecast risk. For instance, cable joint and termination requires electrical insulation improvement. Means cable joint and terminations, you realize it fails because of electrical insulation. So that means in a regular interval, we need to check electrical insulation of these conductors from time to time. Why it is important? Because you are building a system which is more sophisticated on a conventional system. Smart grid is basically building a very modern system on a conventional basic system. If that basic system is not strong, whatever modern you do, when your substation is AC grid is not there, whatever you do is not going to work. So I think this is equally important. And similarly, in case of circuit breaker and disconnectors, benefit from mechanical inspection and survey. So let us discuss comprehensive life modeling framework to evaluate the reliability of electrical components in distribution system under the influence of electrical, mechanical and thermal stresses. The model incorporates empirical aging mechanism, statistical probability function, very two new models. When I talk about physical aging models, the degradation mechanism consider including partial discharge, water treeing, electrochemical breakdown, thermal aging, mechanical fatigue. So the aging follows two principal empirical models: inverse power model, IPM, for electrical and mechanical stress, and then earthiness model for thermal stress. So if I calculate a combined life model, very tough equation, to account for simultaneous stresses, the authors combine these models multiplicitly. Equation 28.1, where electro-thermal mechanical life model of a particular device can be calculated. Means based on those parameters, you can easily calculate the life of any device. So once you know the life of any devices, then the failure, that is statistical model for determining the likelihood of failure of the device at a given stress is compared with the same parameter alpha and can be well described. PL, the failure statistic, probability of failure can be calculated. The Weibull function at the end you see for the probabilistic failure model correlates well with stochastic accidents. So if you do this mechanism, you can also determine the stochastic accidents and whether your function of modeling the failure, they do match. Very important concept, isn't it? So the aging of electrical, yes please.
So, why the difference compared with 63% of this 63%?
Which one?
In this equation, this 63%.
Actually, this is a very standard 2/3 we call it is approximately. L63 is the failure time of a failure probability, 63% as a function of its lifetime. Means the lifetime is 100 years, isn't it? So you are interested to know what is its situation is appearing to 63% of the total lifetime. indirectly reasonably good period. You can take 50, you can take 40, but people with experience, with historical data realize that 63% is going to be reasonably two-thirds of the life. Uh, because it is something like, I'll tell you a beautiful example. If I go for your insurance, health insurance, the moment you are beyond 50 or 45, they don't consider you are eligible for insurance. You know that? Because they know that is based on the average age of living is going to be 60 and one will never die before 45. That is what the assumption. So anyone at 35, 40, they go for, they say, come on, do it, we'll do it. We'll give you discount. The moment you are 55, if I go for insurance, they say, no. You have to pay 3 times of the pay because my probability of failure is very, very high. That's what they say. So it is something like the conductor, when it completes actually 63% of its life, that means the probability of failure become very, very prone. Okay. Now moving to the aging of electrical component is influenced by electrical, thermal, and mechanical stresses. Failure can occur due to overvoltage, mechanical stress, aging, temperature, or time. The characteristic lifetime L63, okay, is used as a reference point to model component failure. That reference point could be anything. So this is what the reference point, based on historically, they might have realized anything below 63, very less likely it fails. Anything beyond 63, most likely it fails. Or all the failures happens after that period, okay? So L63% can be calculated using equation 28.1, which incorporate combined stress effect. And the value of L63% is then substituted in the Babel distribution in equation 28.2. This allows determination of failure probability PL under realistic operation conditions influenced by aging and stress factors. Any messages come now? Okay. Okay. So, what is the question?
What is the typical value of alpha in that equation?
L?
Alpha. What is the typical value of alpha in that equation?
Which equation?
Vehicles.
Just a minute. Here the power actually,
Power of alpha.
it is basically the SEP parameter, represent the component dispersion in time to failure, isn't it? So that value actually depends from system to system. There is no structural value for alpha.
Between 0 to 1 or?
Yeah, it should be. But actually, if you see Australian system, the alpha will be different. For an Indian system, it is different. For Delhi, it is different. For Madras, it is different, isn't it? So it is a system based. Okay. So there is no specific value. That we need to do research and try to understand which function is going to be fitting into this. So once you get 28.3 equation, and then equation 28.3 models failure probability as a function of combined electrical, mechanical, and thermal stress. And temperature has the most significant impact, increasing failure probability exponentially. Okay, temperature is one of the very, very important challenges. Electrical and mechanical stresses also contribute negatively, and at high temperature, insulation becomes so degraded that electrical stress directly causes failure rather than graduating aging. So this is basically a kind of an exponential function, how it fails with high temperature function, okay? And these are the standard equations actually most of the authors have given. And we will come to this point. The failure data in table 1, just a minute. The failure data, the failure table links each failure cause. Example, we are coming to this table slowly, So the failure data in the next table links each failure cause, electrical, mechanical, random, to its corresponding failure location. For instance, paper insulated cable failed due to 60% of electrical and 39% random causes. The total failure probability of a component is computed as a weighted sum mixture of the individual failure probability from all identified causes. That is PL, is summation of AI PI, where AI is the percentage of ith failure cause resulting from table 28.1. That is next table. So here, please, all of you, now someone is asking about alpha. Okay, so this is the table. It could be of any value for different materials or different components. The value of alpha is being defined at different levels. Okay, so they are actually, probably with huge research understanding, these values must have been obtained. And as you say, for distribution transformer, it is 9.9. For circuit breaker, it is 8.3, and so on and so forth. Okay. So all the parameters based on the research being given in this table, which is basically a fitting characteristic to us. So based on equation number, one more question, please.
Which metal is considered the best in the point of mechanical strength for insulation?
Tell me.
Which material is considered the best in the point of mechanical strength for insulation?
Yeah. So we are not getting into material concept here actually, isn't it? We are talking about actually what is prone to the mechanical failure, isn't it? So what is prone to, because here we are not doing research and identifying the type of material, but we are saying actually the mechanical failure. If there is a mechanical failure, what are the challenges and who is responsible? And based on those failure, we will be able to invest our money for making the system more reliable. All of you, please try to understand. You see, if there is a mechanical failure, then we have to maintain. But it is slightly interesting. If you like to give a better material, means you will go for high strength materials, am I right? So, but here we are not interested to identify the material that will avoid mechanical failure. No. What we are saying, for a given component, the failure is due to electrical or mechanical, that we are interested to understand. Am I right? So we are not getting into metallurgy or material sciences here in detail actually. Probably we can do a bit of research, and if possible we can revert back actually which has a larger mechanical strength, but it would not be appropriate for me to comment on the material science and metallurgy at this stage. Okay, thank you. So we'll get into a case study. The calculated probability density of failure are obtained by combining operating conditions with parameters of table 28.1 to 4. These failure probabilistics are shown for various equipments, overhead lines, cable systems, substations, and switch gears. And the figures compare theoretical modeling result with actual operating experiences from statistical data. So this is the beauty, where it is very clearly says, all of you please have a look. You, for example, now first one, 28.1, we are considering a overhead conductor. The x-axis is about 100 years. The y-axis is talking about the probability density function. So we are interested to know the calculated full line and statistical probability density of failure, isn't it? So you can calculate the failures, and you can also do the statistical probability density of failure for each and every year. So if there is a conductor of 100 years, this is how it looks. So what it shows to me, that between 25 to 50, that is close to 35 or 40 years, the device is going to fail for sure. Am I right? The same thing happens everywhere. In case of actually joint cable, you can also draw similar kind of characteristics for paper cable, BP cable, and different type of conductors. Now you can also talk about, secondary housing and secondary substations. The right side is very interesting. You have a distributed transformer, circuit breaker. So for each and every device, based on the historical data, the probability density function can be, and they all looks to be different. And this is what the research component where you need to focus. And we can say, at least based on this, I'll be taking care of those devices more seriously to make my system more reliable. Now, There is one interesting diagram that we might have seen. There are a few diagrams where you see double peak, that is normally, which is very rare, okay? So double peak in failure probability curves for T transformer and D transformer are observed, and these double peak are due to the combined effect of mechanical and electrical stasis, isn't it? So because of this combination, it may fail at this point of time, it may fail in some other point of time also, right? So at the beginning of component lifetime, as you could see, circuit breakers, disconnectors and terminations have been extremely low failure rate. 28.13, whereas it says exhibit, all of you please concentrate, this is very, very important. Circuit breakers, disconnectors and terminators have extremely low failure rate. Okay, as you could see from 28.12. 28.13 shows that the characteristic of transmission transformers and distribution transformers and load interrupters, which have the obvious dependence on component age. And based on figure 28.14, the failure behavior of conductors and of paper insulated cables differs from the increasing failure rate. And these are the tables, as you could see, component, expected failure rate, failures per year, lifetime, standard deviations, and variation coefficients for each and every device has been obtained. So expected failure rates and lifetime of the electrical components as well as standard deviation and variation coefficient are shown in the table 28.5. All failure rates are calculated regardless of the structure of the network, is the dimension of the network is not considered for calculation. Otherwise, it is hard to assess various component among different electric power systems. So what we have learned really, one thing we have understood that reliability and adequacy is very, very important. And to do that, no one can make a system 100% reliable because of limited budget availability. We can concentrate on those devices and we have to distribute our maintenance effort based on the failure of different components. It has been seen in Germany where 20 billion cost is required to maintain a simple grid of Germany itself, very small, 1/3 of this country. And hence, analysis based on 1,20,000 data samples are being obtained across the country, across the world for different devices. And based on those statistical histories, we came to know the lifetime, the number of failures, and how frequently they fail. So based on that, actually, for a given system, I will be able to conclude for electrical distribution system or for a smart grid, what are those components requires more attention, and based on which actually the system can be taken care. So instead of randomly saying you maintain this or that, we had a mathematical calculation based on the historical data, and hence the failure structure being derived, and hence maintenance priority being designed.
Mostly mechanical.
Hmm?
Most reason is mechanical.
Electrical also, for example, cable, it is electrical. For overhead lines, it is mechanical. So it is all together, heating is another effect. And for example, distribution transformers, for example, lead transformers, you see, the lifetime is just 28 years. And we are operating something, let's say, 45 years. And we are saying it is part of the smart grid device. Anytime it will flat. Isn't it? So that is where actually we have to replace immediately if you want to be as reliable. Because for smart grid, we expect the system to be absolutely reliable. There is no comment. So this is just a eye opener. You need not, until and it is relevant to you, you need not spend time on this. But at least the idea of reliability and maintenance in a mathematical and appropriate way must be known to all the people. So expected failure rate, okay. So this is what we have, and with this actually we're coming to an end. And thank you very much for your wonderful attention and interactions. Thank you very much. Bye-bye.
Is there any question, please? So I think there is no questions. So thank you very much, sir. Thank you all. So next class
Tomorrow?
Sunday.
Oh.
Tomorrow.
We'll continue.
So we'll have next class tomorrow, 5 p.m. 5 p.m.
Yeah.
तो थोड़ा पहले करें, 4.
We can do that, but students may be disturbed. Because if you call little early, that we don't have that, so timing, if you change, they will be, we can simply ask, we can take little bit of voting.
Yeah.
Are they comfortable tomorrow or not?
So is it okay if we keep class tomorrow? Are you comfortable? Please, you can type in
Yes or no, yeah.
chat box.
Tomorrow being a Sunday,
Yes.
because if we change the time, then that may suit to some of them, may not suit to others.
Yes.
So very difficult to converge. The only thing is, are they comfortable to have a class on Sunday? If yes, we will have it. Anyone answer? So it seems they are comfortable.
No, sir.
Mhm.
No.
They want holiday tomorrow? Is it? It seems. Okay. And
No. Sunday one already.
okay. All right. So
Perfect one. Holiday, please. 11 बजे रख सकते हैं 26 से मुझे को नहीं रखना ना
26 minutes. This okay.
We are just saying
So considering the holiday on 26th also, so let us meet on 27th at 5 p.m. That's fine.
okay, so we'll have next class on Tuesday only.